Okay, here we are doing, I don't know, one of probably 4 parts. Lesson 17 is a really important lesson. So this would have been our first 3-question lesson on the diploma. If there was a diploma, there would have been 3 guys or 3 questions from this one. So lesson 17 is the first of 3 super important lessons in the course. So it deserves some real time, and we're going to spend some real time. Unfortunately, it's not in class. I miss your faces, most of them. That's a joke, but I do miss most of your. No, I do miss your faces, and I wish we were in class. But this is us making do of a terrible situation. If you have not read this lesson, you need to. So you should put me on pause, read the lesson. You're not going to have did you read, but read it. And so you have some idea what it's talking about. So pause me and then come back. Okay, so I assume you all have read the lesson at this point. So what we're doing is parallel plates, which I talked about quite a bit in lesson 16. So again, there's no really good order to do that in, but parallel plates is like awesome for explaining potential energy lost equals kinetic energy gained, all that kind of stuff. That we did quite a bit of, like accelerating a particle through parallel plates in lesson 16. So that accelerating a particle through parallel plates and potential energy loss equals kinetic energy gained actually came from an example from like physics 20 that you should have done on conservation of energy, which again I would have talked about in class. It's the Tarzan example. It's really good in explaining this. And the Tarzan example was, so this is Tarzan, he's on a platform. Oh, here you get my drawing. And he swings on a vine and his trajectory looks like that. And so this is the ground right here, and this is his butt just kind of grazing the ground, or his feet. So at this point while he's standing there, he had maximum potential energy and no kinetic energy because he's standing on the platform. And that EP max would have come from the maximum height above the ground. And then as he lets go, he's losing height. So he's losing potential energy, but that is perfectly converted into kinetic energy. So potential energy lost, kinetic energy gained. Conservation of energy. At this position right here at the bottom, he's got a maximum of kinetic energy, so that's as fast as he can be going. He's no height above the ground, so all of his potential energy was transformed into kinetic energy. And then of course he'll swing up, and as he does so, he'll gain height, so gain potential energy, lose kinetic, and it starts again. You in 20 then would have had a graph which looked like this. 3 parts to the graph. So you had this part and then a perfect U. Oopsie. That part. That's not pretty. It's not pretty. Oh, that's worse. Okay, this part. And then you would have had a line that went over the top of it. That looks like, no, new color. That looked like this. And this kind of sums it all up. So this is total energy, the blue one. So the total energy in the system is the same no matter what. The red one is going to be your potential energy. So it's at a maximum potential energy over here before he steps off the platform. And then of course your yellow is your kinetic energy. So kinetic energy is 0 when your potential energy is a max. This would be halfway through there, or his swing, where he's got equal amounts of both. And then here he's got all kinetic energy and no potential. And so when we add this position and this position, we get the blue line. When we add the yellow and the red everywhere along the way, we get the blue line. And if you've got that, you're really settled in your head, potential energy lost, kinetic energy gained, and the fact that the total energy in the system is always the same amount, then you can answer any question that I will throw at you that Laura concocted in her fantastic Laura brain, and I will use to test you. Okay, so parallel plates, it's 2 metal plates. They are connected to a battery or some sort of a power source, and that power source is providing some amount of potential or potential difference or voltage. And what happens is that your positives run from your positive terminal and will accumulate on the inside of that plate. Now we typically draw it on the outside just because we're putting particles on the insides of the plate and we don't want to get all these positives and negatives confused. but they will accumulate on the insides. These are negatives. And what's really special about the electric field that exists between parallel plates is that it is uniform. And that is unlike a electric field that is around a source charge. So when we had a source charge and you have an electric field around that, you know that the electric field here is stronger than the electric field here, and that's because the distance is different. And our formula for that was E is equal to KQ over R squared. So your electric field is inversely proportional to the square of the distance, meaning that if you get closer or the distance is smaller, your electric field strength is much larger. So this is non-uniform because it's not the same. What is different about parallel plates is that it is uniform, meaning the electric field strength here is the same as it is here, which is the same as it is here, which is the same as it is here. And people find that very difficult to wrap their head around. The electric field strength everywhere is the same because you can't really measure this in terms of distance anymore. So as you get further away from the positive plate, you will get closer to the negative plate. So distance has less meaning than it does in a case of a source charge, electric field around a source charge. And so uniform electric fields, and again, you should have read this. So electric field between the plates is uniform, meaning that it is the same everywhere. Now the one exception is at the ends here. It gets a little protrudy, and we don't care about that. Like, we'll always be looking at the electric field in between this part where it's like perfectly uniform throughout. Okay, so again, if we were in class, we would build a formula for this. So for electric field strength around a source, we could build a formula thinking about our electric field being that electrified air. And where would the air, or how would the air be more electrified? Well, it would be more electrified if we put more charges on our source. That would be this part of it. So we would say those are directly proportional. And the air would be more electrified if we were closer to the source. And that's where we got this from. Now, in the case of our parallel plates here, if we wanted to build a formula, well, how do you get these plates to be more electrified, or the electric field, to be more electrified? Well, we could jack up the voltage, right? That would be one. So that would be a direct relationship. So if we increase the potential difference, we would increase the electric field. That makes sense. So the air would be more electrified between the plates if our battery was bigger, if we had more juice or more voltage across the plates. And the other would be if we brought those plates close together. So if we shorten the amount of distance between the top and the bottom, or the positive and the negative plate, then the air in between them would be more electrified because these two plates are more bothered by each other. And so the closer the distance, the stronger, or the shorter the distance, the stronger the electric field, meaning that that is a inverse relationship. If we decrease the distance, we would increase the electric field. And this is our formula for the electric field between parallel plates. So you now have two formulas for electric field. This is electric field around a single source charge, where the source is Q, and this is your electric field between parallel plates. And again, if you're not practicing with this, you're going to get really confused with all the E's. There's like 5 E's on that section on electrostatics and magnetism, and you really need to practice what goes where. Okay, this part is what I just said, basically. So this formula can only be used for electric fields that are between plates. That's those uniform electric fields. It does not apply to point charges. To do an electric field around a point or a source charge, you're going to have to use that formula. If you get an electric field using this formula, your units will naturally be in volts per meter because your potential difference is measured in volts and your distance is measured in meters. If you're using this formula, it will be in newtons per coulomb that you will end up with when you simplify all of your units. Okie dokie. You'll read these questions, blah, blah, blah. This is your, you can read those. There's not much to them. All right. Potential difference. So parallel plates are an excellent source of potential difference, which is why I talked about them in lesson 16. and for accelerating particles through some sort of accelerating chamber or potential difference. So to make them go faster or decelerate them, make them go slower. And whenever we're doing that, we're using the conservation of energy. So potential energy lost is equal to kinetic energy gained. They're pretty simple if you're starting them from rest, and a little bit more tricky if they are already moving at a speed when they hit that potential difference. Okay, this part is talking about, it's like blah, blah, blah. If we were in class, well, we are in class, I would say cross all of this out. And what it's talking about is when can we ignore gravity? So gravity always exists. If we've got something like a particle that is dropped off of a mountaintop, for example, there is a gravitational force on that. But because your mass is so tiny, your mass for an electron is times 10 to the negative 31, that force is going to be very, very tiny. And so when we're looking at the interactions of an electron in a gravitational versus an electric field, mathematically, we're allowed to ignore gravity. It still exists. So if you were asked on what forces act on this particle, if it was in an electric field and in a gravitational field, gravitational force does exist. Mathematically, we can ignore it. So we are mathematically going to ignore gravity for our subatomic particles. So for electrons, protons, and alpha particles. All of those alpha particles, all of those are small enough or minimal enough mass that we can ignore mathematically the force of gravity. So this part is saying if it's 1,000 times more, your electrostatic force is 1,000 times more than your gravitational force, you can ignore it. Laura has since said you do not have to do all these calculations to see if it's 1,000 times more, that 100% of the time in the province of Alberta, we will ignore mathematically the force of gravity for electrons, protons, and alpha particles. And for every other mass, we will include it. Okay, so in this case, again, I would read through this. This is not a subatomic particle. This thing has an actual mass, and you've got a charge in here. So if you were doing a free body diagram of your charge in here, and they're trying to suspend this charge between plates, you would have a force gravity acting downwards and an electrostatic force acting up. And your electrostatic force as a formula is on your formula sheet, not in this form, but I had told you at a different, I don't know, video or in class to write it in this form. It on yours is written as Fe over Q on your formula sheet. And beside that, write it in this form because you will use this throughout the course. So what this says in words is this is going to give you the electrostatic force on a charge within an electric field. Now that electric field could come around a source or it could come from parallel plates, in which case the formula that you subbed in here would be different. Okay, and that is going to bring us to Millikan's oil drop experiment. I think I'm going to do this in the next video, and right now we're just going to do that basic questions and the practice problems for that. Here, 1 and 2 in the practice problems will cover what we've covered so far in the lesson. Okay, so I need a new color. I'm sick of this one. There we go. A potential difference is applied across 2 plates, vertical plates, okay? And they're set 5 millimeters apart, which is very tiny. What's the acceleration of a proton placed in the field? And what is the final speed if it started from rest? Okay, so 2 separate questions. What is the acceleration? Well, again, we're ignoring gravity. So our F net here, for calculations purposes, will come entirely from our Fe. And electrostatic force as a formula is QE. So what we end up with is this part. F net is mass times acceleration. And QE, where our E is between parallel plates. So electric field between parallel plates. And so that E formula becomes potential difference divided by your distance. So I'm just subbing in that formula for E. and we're supposed to find acceleration. So Q times delta V over delta D, and that'll all be over the mass of a proton. And then we're just subbing numbers. Again, don't just sit there. You do this. So find these charges on your formula sheet. The charge of a proton is just your basic elementary charge. Your potential difference was given 8,000 volts. Distance was given 5 times 10 to the negative 3 meters. And your mass on a proton, this is on your formula sheet, 1.67 times 10 to the negative 27. Okay. And I'm going to punch all that out. I feel you people not punching. I feel you sitting there waiting for me to punch them. I do. We're kilometers apart and I can feel it. Okay. Oh, the answer is there. Oh, that is right. Okay, so 1.533 is what I get. 1.533 times 10 to the 14 meters per second squared. Okay, so that's the acceleration. That was the first part of it. What is the acceleration of the proton? So again, whatever these plates are, if this is negative and this was positive, it would be like the proton is put here and then is accelerating through here. The acceleration everywhere along those or between those plates would be the same, and that is because the force is the same, and that is because the electric field is the same. And I'll talk more about that in a later video. The second part of it is asking for the final speed if it started from rest. Now, normally if something is asking for a speed, I go right to EP is equal to EK in these questions, and QV is equal to 1/2 mv squared. And I can ignore the initial kinetic energy because there is none, and then I would solve for speed that way. But because this asks for acceleration, I would probably do this by kinematics now. Like, I'd probably do VF squared is equal to VI squared plus 2AD. And if you hate kinematics, then go to conservation of energy, do this, because this is very much a 30 thing, where kinematics is very much a 20 thing. So it's up to you. But like I say, I wouldn't normally do this, but I already had to solve for acceleration, so I'll do this. VF squared is equal to VI squared, which there is none. So 2 times acceleration times our distance. And then, of course, we square root. And I get 1.238. So VF is equal to 1.238 times 10 to the something. Let me see. Okay, times 10 to the 6 meters per second. And you'll get the same thing if you had done it this way. So if you'd done it using conservation of energy, you'll also get that, that VF. You would just need to stick in your mass of a proton. Again, you get that on your formula sheet. Okay, question number 2. We've got 2 parallel plates. They're 6 centimeters apart, and they've got a potential difference of 75 volts. And so I'll draw these ones horizontally because the last ones were vertical. So 6 centimeters across the plates and 75 volts. And of course, that is across the plate, so from one plate to the other. The first question says a proton is placed in between them, and if we move it 3 centimeters parallel to the plates, so that means like the proton is here, and we move it 3 centimeters in this direction, and they want to know how much work is done. And that would be no work. So there's no work because it is not moved this direction. It needs to move across equipotential lines either way, but through equipotential lines. And if it's moving parallel to the plates, then it's moving along an equipotential line, not across them. So no work because no movement through equipotential lines. Equipotential lines. Or you could say not moved through any potential difference, right? Potential difference, to move it through potential difference, again, it would have to be going in that direction. Okay, second question. How much work is done against the field if the proton is moved 3 centimeters perpendicular to the plates? Okay, so moving it against the field, it would have to be moved this direction. So against the field and 3 centimeters. And so again, work is that change in energy. And that formula is QV. So you need to know how much potential difference it has moved through. And this goes back to your proportions and your equipotential lines. We know that 6 centimeters is equivalent to 75 volts. And so 3 centimeters would be how much volts? And that, of course, is half the distance, half the voltage, so you get 37.5 volts. So in moving it 3 centimeters, we will move it through 37.5 volts. So the work is, what is this? A proton with a charge of that moved through 37.5 volts. And you will punch that in your calculator. I'm punching it in mine. And I get exactly 6, so we can't even make it more fun with our decimal places. So 6 times 10 to the negative 18 joules. That's how much work will be done. Okay, and then the last question for today, part C. If the proton is released at the positive plate, so that means it's sitting here at the positive plate, then you let go. At this position at the positive plate, it has maximum kinetic energy, maximum potential energy. It really wants to start moving. So you would have to be holding it there with your particle tweezers. You let go of it and it's going to take off. It will run through all 75 volts of potential as it's accelerating, and it will lose potential energy and gain kinetic energy. So again, our potential energy lost is kinetic energy gained. This is QV or Q delta V, 1/2 mv squared. Rearrange or not, doesn't really matter. You'll get really used to doing this. And then we just punch everything in. So this is a proton, 1.6 times 10 to the negative 19. The potential difference is all 75 volts, and the mass of your proton is on your formula sheet. And you will get a final speed of 119,880. Meters per second, or that, if you want to put it in scientific notation with the right sig digs and all that fancy stuff. That's it. Again, you will do this a lot. This change of potential is equal to change in kinetic. You'll see it right up till the very end. And that's it for this video.